get the bang for your bond with electrons.
It's time to wake up, universe. Okay, hey guys, welcome to Wake Up Universe. We're so terribly sorry that we were a little delayed today.
They're going a little too far with acid.
Yep, we will be doing an experiment with hydrochloric acid today. We have some 1M. The molarity is 1, which means that it is 36.46 grams out of the 36.6 grams per mole of the, well, just to say it's not amazingly strong acid, but it's still been evaporating into the air. You might be able to hear the fan we have in the background, which is because we have been, you know, we sent the acid over there to try and get the fumes out of the room. We got a window open and a fan to try and get a lot of these fumes out. Today we are going to talk about ionic and covalent bonding. What's the difference between them?
Yeah, what is the difference there? I think I heard about it, but what is it?
What is it? I don't know. I mean, it's really interesting. So last week we talked a little bit about ions.
Ah, yeah.
So we talked a little bit about these things. Ions, they are just charged atoms, right? We talked about ions, they are charged atoms. So what does that have to do with it? So actually, let's just pull this table aside. Let's take a look at our periodic table behind us, shall we?
Our periodic table of
science. Sounding like Bill Nye here today, aren't we? So, just a little thing for us. So, let's take a look at the periodic table. So, if we look at these elements, it's really quite interesting the way they're organized. The elements of the periodic table are organized in families, which we call periods. Mm-hmm. They are the up and down, and groups are left to right.
Like that. Groups like this.
Actually, that's incorrect. What am I saying? Okay, so the groups are up and down. Yeah, he's completely right. Groups are up and down. They're also called families, and periods are left to right. But so the basic idea of this, so let's count. Ignoring the transition metals in the middle, because they're weird. Those kinds of metals have a lot of different properties. But if we just look at the metalloids, the stair-step, and everything to the right of the transition metals and these first two columns.
Let me forget these right here. These.
So we have the alkaline metals, the alkaline earth metals. Right here we have what is part of the post-transition metals. They are metals. And in here, the stair-step we call it, in the brown, we have the metalloids. The weirder green, like the one with carbon here, the neon kind of color. The neon green is what we call the polyatomic non-metals. and which fit in with the other nonmetals, which are right here. These are the diatomic nonmetals. That diatomics, it means they come in sets of, like, you know, in the air, it's always O2, you find N2, Cl2, right? And H2 fits in like that. So let's count, you know, and we also have the noble gases left. So there's this thing about atoms. In their outer level, you see, electrons form in energy levels. And energy levels are like a certain ring around an atom. And there's each ring, you know, of electrons. Except for the innermost ring, which only has 2, every outer energy level likes to have 8 electrons. So, let's count though. The outer energy level of hydrogen actually only has 1 electron, right? So it has to have 1. Anything in this first group or family has 1 electron. Anything in the second has 2. Over here we have 3, 4, 5, 6, 7, and the noble gases have 8.
Because because they have 8, they don't really need to have any more electrons. So basically, they like to stay by themselves. They don't really react with anything. These guys will react at a moment's notice because they need to go somewhere. They need to have 8.
It's very true. You see, because these guys, they don't like, and so because these are so reactive that they just want to have that stable octet, what these guys actually do in these first 2 columns is they lose an electron just to have 8. So think about it. So let's look at sodium, for example. Sodium has 11 electrons, but total in its outer energy level, sodium has, it needs to lose 1 more. Sodium's outer energy level only has 1 electron. So what we're going to do is we're going to remove an electron, and then sodium is stable. Sodium has 8, right? So that makes sodium an ion. Sodium likes to lose an electron. So if you lose negativity, negative charge from an electron, it's an ion. So what kind of charge is it? If you lose negativity, it's
neutral. If the protons and the electrons
it's
are
a
together,
positive charge.
If there are more protons than electrons,
See, it's naturally balanced here right now. As soon as it loses that electron, boom. Fits that stable state of 8 electrons in its outer level, but it has 1 more proton than electrons. So that means it has more positive charge. Over here, though, a lot of these guys, a couple of these, O2, S2, but only kind of these guys here, what they'll do, or N2 as well, you know, they will lose 2 electrons. So think, like oxygen. It will lose 1, 2, or I mean, it will gain 2 electrons, and then oxygen has the stable state of a noble gas. But it's still oxygen, same number of protons, but has 2 more electrons than it should. It's O2 minus, because it has a charge that's 2 negative, right? And so what happens is, like, let's look at NaCl, right? We have N plus, because it lost 1 to get that stable state, and Cl, well, see, what actually happens is Cl, because it has greater electronegativity. Electronegativity goes from down here, and it increases going up to the right diagonally. So because chlorine has a higher electronegativity, and electronegativity is the power of atoms to pull on electrons. You see, anything in the upper right has more power to pull on electrons. These elements up here can pull on electrons more. So what happens is this chlorine actually steals an electron from sodium. And sodium gladly gives it up, because sodium wants to have that, you know, that stable state. But it also has, you know, there's first ionization energies, and we can get more into electronegativity and stuff like that a little later. But when we can talk about periodicity. But just for the purpose of understanding now, chlorine has more pulling power, so what it does is it pulls the electron off of this sodium, then chlorine has its stable state, then Na has a positive charge, which is also a stable state, and because this is negative and that's positive, it's a +1 and a -1, they're like magnets. They go to each other. And that's your bond. That's an ionic bond. See, because what happens is, because they have these mismatched charges, they go ahead and they balance each other out, so it's a neutral. This is -1, this is +1, and then you have neutral. When they come together, That is how salt bonds. So anything in these two columns, if it bonds with anything, it is always going to be an ionic compound. Anything these two, most of the time at least. So hydrogen is really interesting because it can do both. Hydrogen can have both, you know, ionic and covalent. I'm sure, like, if I thought of it, I could find a covalent, but like most of the time, metals, anything on the left here will bond down there with something that ends up being negative. So we call these, like we said in the last episode, we have the cations, and then we have the anions, which, so these form cations because they're positive ions. These form negative, which are the anions. Cats and ans come together to make the cation, or just a stable structure. There is no cation. But so, anyways, hydrogen, no, we don't call it a metal. We actually call it, like we said, one of the diatomic nonmetals. So a lot of the nonmetals, though, these can form like other structures. They can form, like SO2, for example, is a non-metallic compound. It's covalent. We have a covalent structure over here. This is isopropyl alcohol. Isopropyl alcohol is C3H8, which is just non-metal structure. It's covalent bonds. Water, interesting thing, as we'll show later, can be either covalent or ionic, because water's pretty weird. Now, most of the time, it's covalent, but we'll explain. You know, covalent bonding is what happens is there's a sharing of electrons. So let's look at oxygen, for example. Oxygen, like we said, it has 6 outer electrons. Although it says 8, right, has the 2 inner ones, and then its outer level only has 6. 2 plus 6 is 8. So oxygen has 8 electrons to balance. But then oxygen needs 2 more to fill its shell, right? It likes to have that full shell. So instead of stealing electrons from over here, because this is not a metal, hydrogen stays. Now, it could work out this way, and we'll explain how when we draw it. But what happens is the oxygen needs these 2, and because of its electron negativity, again, same thing, it pulls not just on the electron of the hydrogen, but it pulls on the hydrogen, the whole thing. And then it drags another hydrogen. So you have 2 hydrogens, and hydrogen only has 1 electron, but how many does oxygen need? 2. So we need 2 hydrogens and 1 oxygen. So what happens is, instead of stealing the electrons, they share them in a covalent bond, a happy sharing family of hydrogen, 2 hydrogens, 1 oxygen. Mom and dad hydrogen and their baby oxygen boy. So
yeah, I like that reference.
So together they share as a family, they share their electrons together. So that is sort of the basics of bonding based on electrons, which is why we said at the beginning. I mean, bonding, it's all about the electron, and it's pretty interesting. The way that works.
And if you try to break the bonding, you're going to get a bang. You know what I mean? A bang for your bond.
It means released energy, which happens in chemical reactions. So, speaking of chemical reactions, let's get to some of those.
Aha!
So,
let's see. Good, Dr. Jerry, what is the plan?
So, first of all, we're going to get our more dangerous ionic reaction out of the way. So first of all, let's just see what happens, shall we? And here I have hydrochloric acid, which I've also diluted with a little bit of water, so it's not quite 1M, because I didn't want this to bubble up in my face. We had it next to the fan. This here is the reason we are wearing the gas mask.
Oh, yes.
I can still see a little bit of some fumes coming off of this beaker. As you can see, that there's kind of some condensation inside of the beaker there. That is not water. That is, in fact, hydrochloric acid. But again, hydrochloric acid, we'll explain, has some interesting things to it. And in here, we have the potassium, distilled water, and potassium nitrate. Always when, you know, mixing things, always use, we have in here dissolved potassium nitrate, same stuff we used in our previous experiments, KNO3. Now both of these are ionic compounds, so let's just see what happens, shall we? So in here, it's kind of hard to see. We should have recorded this so we could have slowed down the reaction. But you could have seen this precipitate that formed, and it immediately dissolved. Now in the air now is also a little bit of nitric acid, but it also sort of dissolved in the water. You can't really see it. I wish I could have slowed it down for you, because then you could have seen the precipitate formed, and we'll get into what a precipitate is. But this in here is both a mixture of nitric acid and KCl, and we'll get into why that is in a moment. So let's just draw that reaction, shall we? I thought it was going to do a little more. Unfortunately, it wasn't of high enough concentration. Tell you what, you know what? We'll want to do it again.
Let's do it again, but we got to be careful.
Let's do it again. We are going to have to be really careful. This is going to be a little dangerous, but we're going to try that again for you guys.
Last time we did this, basically when we opened the bottle, immediately you saw fumes coming out, and it smelled horrible. I can tell you this thing, it made us cough. So basically, you never try this at home unless you have adult supervision, and you have gas, masks like these. And even these don't work that well, so get gas masks if you can. Now, Jerry's basically just right now cleaning out some stuff, and we're about to take out the big stuff.
So,
be careful.
We're going to wash this with Alkanox because we don't want any remains of the previous reaction to still be there. Can you grab me one of the brushes out of the big container there? Or, oh, not that one, the other one. The other big container.
That one.
Or is the other big container? Oh wait, they're in here. Never mind. So we're going to use a test tube brush and some Alkanox to clean this up. We're sorry we added a little bit too much. We wanted the concentration to be a little higher. So we have some Alkanox already mixed up. It's actually a 1% mixture. Maybe I'll show in an episode how to do that. We have to clean this off. So what you do is you rinse a few times with tap water, and then we are going to pour some distilled water in here to kind of get out any of the excess stuff from the
reaction.
So I am noticing that I'm almost out of water in my little jug here, because this just has a pump sink, but we'll try and use whatever I have in here.
But you thought it wasn't a pump. You thought it was real. See? This is good stuff. And so right here, as you can see on the side, just to keep you guys entertained, right here we have a Bunsen burner. This basically is we're going to release gas, and then we're going to use a, basically kind of like a how to say this? Like a slight little explosion when we're going to rub two things together. And that's going to cause a fire. So if you guys want to see a fire, oh my, okay, now we got.
As you guys can see, this is some hydrochloric acid, may be corrosive and dangerous to eyes. So stand back with this stuff. This is never something you should play with at all. I do not want to see any of you at home repeating this experiment. I'm not going to say where I bought it either. This stuff is dangerous stuff, and it's not stuff you want to play with.
No, I can still smell it.
If you ever do this reaction, do it under a fume hood and do it under an advised professional. This is not something you should try at all.
I'm talking about you specifically, buddy. Don't try. I know you're going to try. Don't try it.
We are going to grab one of our funnels just to make sure we don't make any spills here. Have some funnels in here. I'm starting to smell a little bit of a sulfury smell. That is the smell of hydrochloric acid. feel that I almost no, I'm not touching it.
I can grab it.
No, we're not. Alrighty. So, just for safety, I am going to grab it with my beaker tongs here.
It's very acidic, so be careful. Okay.
So this right here, you can see the fumes coming off. It's pretty dangerous. We need to add some distilled water immediately. We're going to add it over here. See how it's a little yellow?
It's not good sign.
Instantly acid. This is still highly concentrated. I need it to be a little higher concentration than like last time. And it is, most definitely is. Turns yellow when exposed to air.
It's good. Look at that. It's pure yellow.
So as you can see, this is a little yellow. It has been exposed to air, which is why this is higher concentration than what we just used. We're going to add some potassium nitrate again to this.
Some serious potassium nitrate.
Okay, so we added the potassium nitrate. I didn't intend on doing this, but we have gotten to this point. So the potassium nitrate, we're going to add some distilled water to dissolve it. Thank you. We're going to dissolve the distilled water, or dissolve the potassium nitrate in distilled water. And we'll explain why we're doing this a little bit later. We're not only diluting the concentration, but we're making the reaction possible. We'll describe why in a couple of minutes. You see, because this isn't just a simple ionic bonding where we have two ions and we put them together. See, ions just don't exist naturally in nature. The reactions happen so instantly. You can't just get an ion. You would have to make it in a lab, and we aren't quite... there are some reactions we could do, but we haven't done any of those. We're going to add a little more distilled water. I'm quite positive that it was just because we didn't have a high enough concentration of the sulfuric acid. But what we're going to do is we're going to try and really dissolve this stuff in there. As any excess isn't going to react. We want to get as full of a reaction as we can. So if you look on that bottle, you'll see it says contains potassium nitrate. So this is about as dissolved as we are going to get. I add a little bit too much potassium nitrate, but here we are. We have the potassium nitrate as stirred up as we can make it in here. And I still see fumes coming off of my our acid right there. So I am going to add, we're going to need a bigger beaker. Need another beaker. Something else wash this.
While we are waiting for Jerry, just want to advertise these. These are the custom-made Jerry Bear mugs. Right here at Wake Up Universe, as you can see. I really encourage you to try out one of these. You can just contact us and buy one. These don't cost that much money. And if you enter into our contest, which we will be doing, you might be able to earn a free one. So I would encourage you all.
Add quite a bit of alkanox. We'll do the reaction inside of this very big, this is a 1 liter beaker that I got. We'll try and clean this out. I had some salt water in here, but we're not going to do that experiment anyway.
The fumes are still leaving.
So just to kind of show off, we are using Kroger brand distilled water, anything you can get at the store. That's not the best. It's best to distill your own. Of course, we don't have a distiller here. You can easily buy one.
Only at Kroger.
Well, you can't buy the distiller at Kroger, but the water is only at Kroger. I mean, you can get other brands at other stores as well. Kroger even sells other brands of distilled water, I believe. So we're just using the, oh, we have had a little bit of a spill here, which is not a good thing.
Good thing is, it's only water.
Yes, this is only water.
If that was
Now
acid,
we gotta
would
make
probably
sure we don't miss on the acid.
If that was the acid, oh no.
So we are going to clear up. We're going to do the reaction in here. And we both will kind of mix up again our little aqueous solution here. And that is what the acid is as well. The acid comes dissolved in water already in the bottle. You dilute it by adding the acid to water. Not really the other way around. That's not the way we did it, just because we're in a little bit of a rush here. That's the way we did it earlier. So what we're going to do is we're going to pour the both of these together, and hopefully we'll see the reaction. We'll try and clear it. We'll put it in the front here for you. You'll see that a precipitate formed at the bottom, just as I had hoped for. It is already dissolving, but if you see the cloudiness in there, that's because there was a precipitate. You can kind of see in the bottom, if you look closely, that there is this little substance that has formed at the bottom. This white substance is potassium chloride. And in the solution, the aqueous solution, we have nitric acid. So let's explain what happened there. Because why did we put two liquids together and there's a solid at the bottom? What is this? What is that? So, first of all, I'm going to take my two little beakers and put them over here. Along with this beaker, as it has nitric acid in it. We don't want to have that around. So, what happened in that reaction? Let's do some drawing, shall we? So, we have ions, right? So we talked about ionic compounds a little bit last week. I believe so. I can't quite remember what we did last week. But so, ionic compounds. So let's look at the reaction that we had here. First of all, let's look. We talked about ions, right? Hydrogen in that first category is going to lose an electron, making it H+. Just as we talked about HCl, right, last week. HCl is H plus Cl minus. So those two come together because chlorine stole the electron from hydrogen. Together they're HCl. Now, we have to make it aqueous. Aqueous, what that does is it separates the H plus and the Cl minus, as we drew in the last episode. We talked about pH. pH parts hydrogen. The more parts hydrogen you have, the higher strength the acid. Now because this has 1 H for every Cl. It is a fairly strong acid, the pH. We can test the pH. I don't have any pH paper with me right now, but the pH is going to be, probably with that paper, which isn't the best detector, probably like way down there around 0 and 1. It's really low pH. Probably no, 1 around there is probably what it is. So what we also add that to is in a reaction, we add KNO3. KNO3 is also aqueous. We try to dissolve it in distilled water so there's no impurities. KNO3, so we have K plus, and together this is called a polyatomic because it's an ion, as we said last week, NO3 minus. So NO3 minus takes the electron from the K, which is potassium, making it KNO3. Well, what happens in this reaction? We have the HCl and the KNO3. This is called a double replacement reaction.
A switch.
Double replacement. So they switch, just as Sebastian has said, they switch their anions. So what do we have?
Okay, so first of all, we're going to have a switch specifically with HCl and KNO3. Now right there we're going to have HCl, where we're going to have H, but instead of having Cl, we're going to have an NO3.
Now because these are both plus, this one's minus, that one's plus, they both neutralize charges. And what else do we have?
And on the other side, we're going to have Cl and a K. So basically, chlorine and potassium together, because they're both opposites.
We have
K and then Cl.
We have KCl. KCl is a salt. That is the precipitate we saw that formed. So that is a solid. So the HNO3 is still aqueous. Same thing. Instead of Cl minus, we have NO3 minus in here. And that is what happens. This is the reaction we have. HCl. So what happens is the H and K switch places. They switch their anions, and we come out with HNO3, which is nitric acid, which is also kind of going into the air right there, which is why we put it by our fan. And then we also have KCl, potassium chloride. Has 2 S's. I don't quite have enough space there. Potassium chloride. So this is a salt. It's been used on roads in the past, but also the most commonly used one is CaCl2. See, because Ca is 2 plus, right? We look at our periodic table. Ca needs to lose 2 electrons. Ca 2 plus, and Cl. So we need Cl minus. So we need to have 2 of those. So CaCl2 is the most common. Calcium chloride, the most common for salt on road. But KCl, potassium chloride, has been used on road as well. The regular table salt, NaCl, is not very common. It's Na plus Cl minus. It's not commonly used on roads. They call it a salt. Pretty much all these like chlorides that form with metals, we call those salts. MgCl2 is another one. Mg2 plus, Cl2 2 minus, because it's 2 HCl's, or 2 Cl2s, that is. So that is our current status when it comes to ionic bonding. Ionic bonding is always because of charges. Opposites attract, as you were always told about magnets.
And love. And love.
And love. It's how reactions work. It's how we do it, and that is ionic bonding. So let's take a look at what we have in here. So we're going to light our Bunsen burner now. Now actually, first let's talk about water. So water forms H2, 2H2 actually, plus O2 creates 2H2O. Alright, so let's count. We have 2 oxygens, right? 2 H2s, right? So now we have our water reaction. This is actually what happens. Hydrogen burns. So hydrogen will burn, therefore making it oxidize with the oxygen, the air, O2, making H2O. This is the covalent way to look at it when hydrogen burns. But also, we have H+. Last week we talked about pH. We said a possible anion is OH-. So the H+ and the OH- come together. We have HOH, charges are neutralized. And also, instead of HOH, we have H2O. So water can either be an anion, or, I mean, it can either be covalently bonded or ionically bonded. Most of the time, just because of how common it is to have ions like that around, actually, that's what happens. That's why, let's say we look at, what did we do last week? If you put vinegar, which is H, C2, H3O2, plus the, what we had, we drew the reaction last week, we had, what did we add it to? We added it to baking soda, which is sodium bicarbonate. Of course, they switch and they do their little thing. The acetate switches with the HO3, and we have CO3. It separates into, as when you mix acids and bases, something they'll always make. They always make a salt. They always make, they usually, always have a precipitate, and they always have water, right? H2, we take an O, right? And then the CO, instead of 3, it's CO2 because it lost an oxygen to the water. We have H2O and CO2. So water is always formed when mixing acids and bases. So that's that. Now just remember, ionic compounds don't necessarily have to be acidic. NaCl is not acidic. It is just salt. So, yeah, that's that. I'm going to put away our hydrochloric acid because it is...
hydrochloric acid.
It is. I can smell the fumes still in the room, so I'm going to put that away. We're going to look at... Next, we're going to look at the possible covalent bonding we have here. So in here we have isopropyl alcohol. It's 91%. This is typically used for first aid things, but it also burns. See, it says highly flammable on the bottom. It is fairly pure alcohol, not completely. And it is C3H8. What we're going to do is we're going to light our little Bunsen burner here.
And just to make you guys understand specifically what we're going to do, this basically says, do not burn it. And we are going to burn it.
It says highly flammable. It's not supposed to be for burning. And we don't follow all the rules. Obviously, we have hydrochloric acid, and we're not supposed to do this at home. Please, ladies and gentlemen, do not do this at home. This is, do this under parent supervision. If you do, make sure you ask them. The hydrochloric acid, if you have some crazy parents, you make sure and tell them this isn't something they should be doing at home either.
Oh, no.
Even if it is your parents. So what we're going to do is we're going to light our Bunsen burner. I can...
Now you're about to hear a weird sound, and bingo, now we have
So now we have a flame.
See the blue flame right there. Ah, now it's okay, that's it.
So there we go. We have our gas, and it is going, and have our Bunsen burner. So what we have here is I have this little setup, a little paper clip, and a piece of wood. I'm going to try not to light the piece of wood on fire, and just burn the alcohol. I kind of have the alcohol film in a little loop right here, and we're going to see that it... Oh, wait. So you guys saw that that lit on fire. So alcohol is highly flammable. It has a burning reaction, and we'll show you what happens. So alcohol lights pretty instantly. The stick is not burning, the alcohol is. So that is the burning of alcohol. So that is one of our reactions here for you. So that is what happens when you burn alcohol. So let's draw the reaction on the board. Alcohol burns. What happens? So burning always has the same products. We have it's like the oxidation, they call it a combustion reaction.
Combustion meaning based on exothermic reaction, you're going to release energy, and we're breaking the bonds and reforming them to basically our products.
So that is the basis of this. So let's look at what happens here. We have C3H8, which is the isopropyl alcohol. This is, believe it or not, alcohol is an organic compound. See, because what happens is, like, the way they make alcoholic beverages, they stick yeast and some sugar or some kind of sweet, something that has sugar in it, like fruit, and the yeast ferments it, or what the yeast just digests it. it eats the food, and one of the byproducts of yeast, which does, and we can talk more about this later, they do anaerobic respiration. Anaerobic respiration creates alcohol as a byproduct of their digestion. So what we have here, isopropyl alcohol.
Don't take a piece out of me for distillery.
Oh yes, no distilleries, please. Parents only. So C3H8 plus, we have O2, right, in the air. And so what that's going to do is it's going to produce for us the same things that we always have. We have CO2 plus H2O because, so let's just count this. Let's make sure. We're going to have 8 hydrogens. Do we have 8 hydrogens over here? No, we don't. So we're going to make that 4H2O. That means we have 4O. This is balancing equations. We have 2O2. We have 1, 2, 3, 4, 5 oxygens. Now we don't want to have that either. So we have 3 carbons though, and only 1 here. So if we make this 3, we're going to need to do that here too. Or no, we're not. So we have 8 hydrogens. Do we still have that? We have 8. So 4H2, we have 8, right? And then we have 8. Okay, oxygens, we have 4, and we have 3 times 2 is 6. 6 plus 4 is 10, which means we need to have 5 O2. So let's see if our equation is balanced. We have 3 carbon, right? 3 CO2. 8 hydrogen, yes. 4 H2, yes. And we have 5 oxygen. So we have 5 O2, so 10 oxygen. So 3 times O2 is 6 oxygen. 4 times O is 4. 6 plus 4 is 10, which is 5 times 2. And this is the balanced equation. So C3H8 plus 5O2 goes to the 3 CO2 plus 4 H2O. And also, we have heat. It's a byproduct. So what happens is the bonds within these have less energy than the bonds that were made in here. See, because H2O is actually fairly weak. We just have those simple little covalent bonds. Breaking water can actually just be done with a little, which we were going to do today, and just be used using a little electric charge, like a little battery you can buy in a store, like a 9-volt battery, will separate water. So obviously, they're not very strong bonds. With this, it takes heat to make heat. So we have 3 carbons, right, bonded to 8 hydrogens. Hydrocarbons have a really strong bond. They have a lot of energy in their bonds. And so look at all of these bonds here versus just these 2 weak little bonds. So that all the energy is released from these bonds as heat, and some of it is stored in these guys. So that is the essentials covalent bonding. We'll kind of draw a picture of the difference. And so let's kind of get down to the final basics, and we'll go up and wrap up, and we'll get to today's cash craze.
But so basically, you guys can see right there, the reason that we have to have the equation balanced is because of the law of conservation of mass. Basically, mass can neither be destroyed or created. Except, of course, for equals mc squared. Right? Forget that. Forget Einstein. Basically, mass, when we're going to have mass in a reaction, the same amount of mass must be on the other side.
Yes. So unless, now this doesn't have